We now want to use Snake Lemma to prove homology long exact sequence. So consider this chain complex A. So you have the sequence of modules an plus 1 going to an minus 1, index is decreasing, and then you have these maps D. And only thing you need to remember is that the image is contained in the kernel. So at every module, the image of the map coming in is contained in the kernel of the map going out. So recall the definition of homology. So say you want to compute homology here. So homology hn minus 1 is kernel of the arrow going out dn minus 1 modulo out the image of arrow coming in image of dn. So this kernel of dn minus 1, you write it as zn minus 1, that is 0's n minus 1, because kernel means mapping to 0, and image of dn is nothing but dn applied to an. So this you write as d of an. So in fact all these maps we forget the subscripts and write them as d, because when we refer to as homology at any point, this is just kernel of arrow going out over image of arrow coming in. So you just know, looking at the module, what the map is coming in and going out, and you can compute homology. Therefore we do not write these indices. So this is d of an. So this d of an, you can write it as an modulo out d of an plus 1. So why can we modulo out this portion d of an plus 1? That is precisely because this d composed with d will give you 0. So this is anyway 0 if you apply d to it. So to see this, so consider an element x here. So this x will get mapped to dx right here, but this will get mapped to 0 here, because this is an image. So this is an image. So if this is an image, it lies in the kernel of the next map. So it lies in the kernel of the next map, kernel of d. So when you apply d to it again, then you get 0. So d applied twice gives you 0. D applied twice gives you 0. And that is precisely what we are using here. So this x gets mapped to d of x. So this d of an plus 1, all the elements which are in the image, they lie in the kernel, so they become 0. So instead of dan, we can write this, because this is anyway equal to 0 for our purposes. You know, why are we writing like this? Because we need this form. So consider this map here, an over dan plus 1 to zn minus 1. So basically this denominator I am copying right here, and the numerator I am copying here, and this is the map d. So basically that means this is the cokernel of this map by definition of the cokernel. So cokernel of d is now hn minus 1. So we have redefined hn minus 1 as the cokernel of this map just by defining this map like this. So what have we done till now? So we have a chain complex. From this homology chain complex, we just isolate this particular map, and we say the cokernel of this map is the homology group. So rather than the direct definition, we are saying the homology group is cokernel of this map, which this map looks like this. What is the kernel of this map? This is what we have to check. So what is the kernel of this map? This we want to check. So we will come to this. So now recall what is the homology. So homology we have to compute here. So kernel of arrow going out over image of arrow coming in. So kernel of dn over image of dn plus 1. So instead of dn, we can just write d. So this d is obviously acting on an. So you have d of an over d of an plus 1. So kernel of d of an over d of an plus 1. Now we just write d outside instead of here. So d of an over d an plus 1. So you can write like this. So this is precisely the kernel of this map here. So kernel of d is what? This is homology. And we have done absolutely nothing. We have just rearranged terms. So notice that we have taken kernel here first, and then we modulo out by image. And here we first modulo out by dan plus 1 and then take the kernel. It doesn't matter, because this d will anyway cancel out with this d. So doing it first or after does not really matter. So this makes sense. So this makes sense. So you have to convince yourself. So just remember d square is 0, and everything else will follow. So now we have two things. Cokernel of d is hn minus 1. Kernel of d is hn. So kernel of d is hn, and this comes from the chain complex. So now consider this short exact sequence of chain complex. So 0 to chain complex A, then you have another chain complex B, another chain complex C, and 0. So A we have already given like this. So similar to this you will have B, and similar to this you will have C. So corresponding to this A, we have constructed such a map whose cokernel is Hn minus 1 and whose kernel is Hn. So consider this diagram. So this particular thing we already have shown. So this corresponds to chain complex A. It comes from right here. Corresponding to B, chain complex B, same argument, you will have this complex, and corresponding to C you will have this complex. What we have not shown is that these green arrows are exact. So suppose that these green arrows are exact. So our green arrows are exact. So you suppose that. And we will show this later. So we will show this later. For now, assume that this is true. Now if this is true, then you can use your snake lemma. So that means kernel of dA, kernel of dB, kernel of dC to co-kernel of dA, co-kernel of dB, co-kernel of dC. So corresponding maps. So you get this. But notice that what is kernel here? This dA is this D map here. So kernel we said is this Hn. So this is Hn of A. And what is the co-kernel? Co-kernel we said is Hn minus 1. So this is Hn minus 1 of A. Similar argument to B. So you get HnB here, Hn minus 1B here. Similar argument at C. You get HnC here and Hn minus 1C here. So you get a long exact sequence of homology groups of this chain complex by using snake lemma. So now we have to show this, that the green arrows are exact. So first we will show exactness here. So we will show exactness right here. So exactness here follows from exactness here. So notice that this is the map between chain complexes. This is chain complex A, B, and C. So this is Dn minus 1 here for chain complex A. This is for chain complex B. This is for chain complex C. So these are homology complexes. So you're going from n minus 1 to n minus 2. Your index is decreasing. So in the proof of snake lemma, we showed that if you have this map of complexes like this, then you can form the kernel here. So this is kernel of dA n minus 1, kernel of here, kernel here, and we put a 0 behind it like this. So this exactness we showed in the proof of the snake lemma, and this by definition this is nothing but Zn minus 1a, that is zeros, because it's kernel, so zeros at n minus 1 of a. This by definition we write it as z of n minus 1b. So by definition we write it as z of n minus 1 c, and that's precisely this here. So we have shown the exactness of this bottom row. So now we show the exactness of the top row. So now we focus on this top row. So again, consider the chain complex corresponding to A. So this is homology complex, so index is decreasing, index is decreasing, index is decreasing. So again we showed in the proof of snake lemma that this co-kernel which you form like this, an over image of this map an plus 1, bn over image of this map, cn over image of this map. So this is exact. So in the proof of snake lemma we showed this part, that these co-kernels which we form are also exact. So this exactness comes from the proof. So this you copied right down here to show the exactness. So we have shown the exactness here, and therefore we can apply the snake lemma to get the long exact sequence of homology.